which has DNA as the basis, and changes in DNA giving rise to different species, different organisms. This was unraveled by Francis Crick and Jim Watson and Rosalind Franklin and Maurice Wilkins, who made major contributions, are shown over there. So let's quickly run through how all of this took place, how evolution took place. As I said, about 3.5 to 3.8 billion years ago, we had simple cells, prokaryotes, and about 3 billion years, something again fantastic happened, which is photosynthesis. The source of energy, which I talked about, which powers us, which powers the brain, from sunlight became possible. And this was an absolutely dramatic change. Energy was there for free. And you could have organisms which synthesize this energy, and other organisms which ate these organisms, which could thereby have energy. Right? And we had complex cells 2 billion years ago, and multicellular life about 1 billion years ago. About 600 million years ago, you had simple animals, and you had arthropods, ancestors of insects, arachnids and crustaceans about 570 million years ago, and complex animals about 550 million years ago. And this huge complexity came about in something called the Cambrian explosion. And look at this. You have these depictions of animals which can eat and put stuff out, move around, and they have heads, they have tails, they have limbs, and so on and so forth. And this body-plan creation, again, has a shared mechanism. This is something which went on for a while, but another dramatic change came, and that was the onset of flowering plants, which is about 130 million years ago. And amphibians and so on came much earlier, about 360 million years ago, and mammals about 200 million years ago. And 200 million years ago, while there were mammals around, we did not exist in the way we are. And the kinds of mammals were small mammals running around. And the world was dominated by reptiles and other animals, cold-blooded animals, such as dinosaurs. Some of them might have been warm-blooded. And this is a picture of reconstructed dinosaur at the Indian Statistical Institute. It's called Barapasaurus tagori, and it was put there by Pamela Robinson, shown there below. 65 million years ago, something rather dramatic happened. And an asteroid hit the Earth. And this stroke of ill fortune or fortune, depending on what you were, if you're a dinosaur, this was a slight problem. This completely caused enormous climate change and eliminated dinosaurs and a very large number of other animals and plants and so on and so forth. This is just 65 million years ago. Thank you very much. I'll keep it down there. So the result of this was an opportunity for the mammalian radiation to burst out. And that happened rather dramatically after that. Something rumbling?
See where the sound is coming from.
Yeah. So after this attack by the asteroid and the death of dinosaurs, extinction of dinosaurs, we had about 2.5 billion years ago the appearance of various kinds of hominids. And sound gone off? Yeah, hominids. And it's about only 200,000 years ago since the appearance of modern humans. And only 25,000 years ago since Neanderthals, shown illustrated here, died out. And we have in us DNA from Neanderthals, from Denisovans, and from other hominids. And there was a time, not that long ago, when there were many different kinds of humans, as it were, on this planet living together. And now, today, we have only Homo sapiens. Right? But our brains, the Neanderthals' brains, the Denisovans' brains, were apparently not that different from ours. They had peculiarities which made them distinct, but they were not that different. Our brain size 25,000 years ago were no different from the brain size now. Yet, we do things now which we didn't do 25,000 years ago. For a long period, we made fundamental tools, drew rough art on caves and so on and so forth, and nothing much changed at all. What happened? How did a major change came about which allowed us to be the way we are now? What allowed us to go from taking small rock tools and hunting and gathering and managing to survive into doing something like this? Right? There's no change in our body, there's no change in our brain in capacity. This dramatic change came about because of cultural evolution. And the rate of change of cultural evolution was been absolutely stunning and began about 10,000 years ago. What happened 10,000 years ago? Around that period, all over the world, in many different locations, we had a situation where people domesticated plants and animals. There was a density of population, and people were packed closer and closer together because of that. That resulted in even more domestication of plants and animals. And people moved, therefore, from being hunter-gatherer dispersed societies into more intense societies. Fire had already been discovered. That had much earlier allowed the packing of huge amount of protein into one meal. So unlike our gorilla and chimpanzee relatives who have to constantly eat to keep their brain well fed, our brain size, disproportionately large for our body size compared to other primates, could get high caloric inputs by packed meals because of fire. Right? Something else happened along with our density of population, and we don't know exactly when that happened. It perhaps happened before, certainly happened before communities started forming. And one was the ability, which happened a long, long time before that, was our ability to oppose thumb and forefinger, and therefore to hold and to make tools. So that in itself was not enough. Our voice box is distinct and different from other primates. That allows us to make sounds. And as a consequence of these, our brain areas which process this information also perhaps became wired in a different manner. The result of this is a computing system, a hardware, which already existed and was there for a long time, became amenable when certain software developments took place. What was that software? That software was language. Language and communication and technology as a consequence completely changed the use of this hardware. And just like genes and DNA allowed the propagation and evolution of species over millions and hundreds of millions of years, the evolution of software, what Richard Dawkins called memes, resulted in the evolution, cultural evolution of humans in a much, much more rapid way. Right? Language, communities, art, science, technology, space flight, all of this took place literally in the last few hundred years. I mean, these kinds of things in the last few hundred years, but everything else in the last few thousand years. So it is this over-designed computer which evolution allowed to take place. And on that, the emergence of software through a series of accidents has made us what we are. The hardware is essential. You couldn't do it with just that software. But without that software, you wouldn't go anywhere. So the question comes, if this is the case, why is it that, or what is it that is similar between us and other organisms? Can other organisms sense the world the way we do, or are they intrinsically different? When you stand before a painting or you listen to music, you think about, you see the kids, you think about them, and then your mind wanders, you think about relatives who are similar, and then you think about the parents of the relatives or your cousin, or when you visited some other place, and your mind wanders to all these complexities, and you think about all of that. Imagine if instead of you, there was a chimpanzee or a monkey or a dog watching all of this. Does it have the same capacity to think about its life, its past, its future and present? And the short answer from what we know today is no. There is an unusual human capacity which has allowed us to move in a different manner, and that seems to be, while there is a linearity and a connectedness in the hardware, the scaling of that hardware to form a huge number of parallel computers from the simpler units which are there has resulted in the ability, along with other external sensory mechanisms like making tools and voice and so on, in the evolution of language, communication and technology, which makes us very distinct. Right? Now, how do we know all this, and what can we learn more? First of all, I should say that we know very little, and what we have learned so far is only the tip of the iceberg, as it were. We need to learn a lot more, but I think we are on the path to understanding which is dramatically different because of advances over the last 20 to 50 years. First of all, because of the connectedness of all life on the planet, the fundamental building blocks of making a complex organism, such as a human on the right or a fruit fly on the left, are exactly the same. The toolkit which is needed to make a complex organism, a small aeroplane, for example, screwdrivers, nuts, bolts, rivets, materials, are exactly the same as needed to make a huge A380. You use the same toolkit, you use the same components, but what you do downstream, the kinds of scaling you do and how you put them together, whether you're making a hut or a skyscraper, you do different kinds of things, but fundamentally the toolkit is the same. And fundamentally the higher level toolkit to make a fly and a human are same in terms of the kinds of molecules. So therefore, when you learn about how to make a fly, you learn about how to make a human. You learn about how to cure cancer by studying a plant or a bacteria or a fly, and also by studying cancer. You learn about mental health by studying how cells communicate with each other in any organism. You learn about mental health by studying brains in any organism. So this connectedness at the molecular level is something very important and widespread. It doesn't tell you how a human works, it tells you how the components which are used in a human work. Anyway. A component of the brain, which is absolutely important, of course, is the nerve cell. And understanding how that works is also common to a variety of organisms. Now here is the giant squid. Using this giant squid, Hodgkin and Huxley, two British scientists, took out the large nerve cell from this squid, squeezed out the inside, and replaced that with saline, and then started putting in specific components, poking needles into that, and asking, how does a normal nerve cell work? A normal nerve cell, when it's stimulated at one end, sends an electrical signal and sends out a chemical signal at the other end. How is this electrical signal generated and propagated? And that fundamental insight came from Hodgkin and Huxley recording a single nerve cell. Now, you're talking about a single nerve cell. How do you ever understand how 86 billion nerve cells work in a human? That ability is increasingly becoming feasible by techniques which allow us to look at the physiology and the functioning of tens, hundreds, thousands, and soon much larger number of nerve cells together. And these are ways by which are called optical recordings of nerve function which can take place. So, to summarize this part, biologists do three things. They always ask only three questions. Where does it come from? right? And that's evolution. And I told you about how we evolved. How is it made? That's development. And I told you that development, the tools are conserved, right? So you can study development in plants, animals, and so on and so forth. And how does it work? That's physiology, which I showed you over here. Looking at these three things, one can ask, how is the brain set up to allow our higher mental functions to emerge? Right. Now, you can understand the hardware better and better and better. You can understand how nerve cells talk to each other. But we still don't get from that approach understanding how complex behavior, complex thoughts emerge. And the answer to that is coming because we are learning now that there are different parts of the brain which are specialized to do and respond to different things. Signals from the outside go, and there's both output to movement, but different layers talk to each other. And one of the key features of complex brains, and this complexity is there in insects also, is the layering of information flow. I can think about this glass, but then I can think about the fact that I'm thinking about the glass, and I can think about the fact that I'm thinking about the glass, and so on and so forth. This recursive way of doing things and feeding forward is unique to higher complex brains. Flies do that when they have to move and evade and swat things, and they have memory and learning and habituation about what they've learned. So, for example, when the wildebeest sees spots in the African savannas, it doesn't sit and think, spots could mean a bedsheet, it could mean a leopard, it could mean that something paint has fallen there. It just bolts. And the reason is, it does that first, is it has been trained to make guesses. We hypothesize about the state of the world around and act on it instantly. We don't analyze and do this as a single nerve cell does or multiple nerve cells do and then act on it. So this ability for multiple disconnected units, disconnected functionally, but connected, loosely connected functionally parts of the brain to act with speed through guesswork based upon experience is something which is unique to brains. And this is very important for movement and for survival. Now, one of the most famous philosophers of the brain, and there's a group of people who study the brain now, these are neurophilosophers, they combine the understanding of neuroscience with the understanding of the brain. And so the study of consciousness, which till recently used to, and about complex behavior, which till recently used to be the purview of old scientists who don't have anything better to do, fools, or lunatics who think that somehow they can solve this problem, has changed dramatically to being an area where serious young people are getting into. So one of the most famous neurophilosophers is Dan Dennett, and this is at a symposium in Dublin some time ago. Dan Dennett sadly died earlier this year, and Dennett and a group of philosophers have come up with various kinds of theories of how complex behavior and abstraction and consciousness emerge. So there are multiple theories, multiple views, and they're summarized very nicely in a book by Anil Seth, which I recommend you read, and how these theories are useful and contradictory or not summarized there. But then it points out something which is very important. And I'll quickly go. Anuradha, how much time do you have? I'll finish.
Less people will leave, so let's go on. You have to leave.
So Derek points out something which I mentioned earlier about what happened some time back. 10,000 years ago, humans and our livestock amounted to 0.1% of terrestrial vertebrate biomass. right? You're not talking about fish and so on and so forth. But terrestrial vertebrate biomass, other mammals, reptiles, cats, bats, all of them, we amounted only to 0.1%. Today, humans, our pets and our livestock amount to 98% of terrestrial vertebrate biomass, mostly cattle and chicken. Yeah? This has completely changed. So Dennett says, over billions of years, on a unique sphere, chance has painted a thin covering of life. Complex, improbable, wonderful, and fragile. Suddenly we humans have grown in population, technology, and intelligence to a position of terrible power. We now wield the paintbrush. So we are in charge of the planet now in a manner which no other species has been. And this is dramatic. And how has this happened? It's not that complexity and complex behavior is a purview of only humans. As I said, the software and the capabilities we have are what make us unique. And Dennett gives this interesting example. On the left is a termite hill in Australia. And on the right is a cathedral by Gaudi in Barcelona. This has no central command. There's no one in charge. If you open it up, it's as complex as that. No termite knows what the other termite is up to. There is competence without comprehension. Right? And that is the way complexity arises in much of nature. Competence without comprehension. Humans are unusual in that they combine competence and comprehension. And this is a dramatic change. But humans have done something else now. It's not that we're just like bacteria which can sense and respond, right? We have got the ability, because of this single neuron communicating like a termite does with other neurons. And these 86 billion nerve cells in our brain are like termites, to use a metaphor. They do not know what other cells are doing from the context of purpose. There is no purpose at all in this brain. Yet, these 86 billion nerve cells have resulted in not just competence like a termite hill, but also in comprehension because of the kinds of software issues that I told you about. And this is a dramatic change which we've had. So, this is a blank slide, so that we can, when I show this blank slide, the IT people get worried that it's gone off. But it's just so that we can talk without getting distracted. So you have a brain of 86 billion nerve cells, analogous to a termite hill. Each cell essentially they're communicating with each other, just like termites do, but they don't know about any general purpose. They don't know that the brain has to solve an important theorem in algebraic geometry, right? Yet, the brain does that, right? How does it manage to do that? Fundamentally, can we learn something from smaller brains and how that is done? No, overall, it seems the way the brain does these kinds of things layers on this software, and the rate of change of that software has been moving dramatically forward because of both our language, our culture, and various kinds of prosthetics. The kinds of prosthetics we have developed are absolutely stunning. So I no longer have to feel bad about my poor ability. When I enter a thermodynamics class, I understand everything. When I leave Balu's thermodynamics class, I forget everything. So why does that happen? I mean, that's a problem which I have. But with this, I can constantly remind myself and overcome that deficit. I can learn many kinds of things. I mean, some people are good at navigation and they don't need this, but other people need this for navigation. So this development of prosthetics has been amazingly transformative, whether it's our spectacles, our cane, or our telephones. In that situation, what can we learn about what is happening in the world of artificial intelligence, for example. In principle, you are getting, and in practice too, more and more complex machines which can analyze data and take decisions based on what has already happened. That works pretty much in a way similar to how the brain works, by having multiple layers communicating with each other, feed forward and feedback. And by training, you put weights to different outputs, and the result of that is something which satisfies reality. And you know that this artificial intelligence wildebeest will also run away from a spotted sheet thinking that it's a leopard, because it's been trained to do that. But will it have the possibility of comprehension and abstraction and culture and language which humans' brain have? Is it theoretically possible? And the short answer is, theoretically it is possible. There's no reason to think that if I didn't have an arm and I put a prosthetic which has all the sensory and motor information that an arm has and connect it to my spinal cord and to my brain, that this arm, if everything is in place, will behave like an arm. And that is indeed true for, whether we like it or not, for more complex parts of our brain. So in principle, a machine can do everything. Whether it should be allowed to do that, what are the precautions, is another matter. One area of the brain which is very important for us to move around in a coordinated manner is the cerebellum. And people with defects in the cerebellum have defective motor control. Interestingly, people with no cerebellum at all because of a developmental defect seem to be able to get motor control of a very high level with prosthetic tools of various kinds, which they can use their sensory input to use this for motor output, and they can be trained by various kinds of prosthetics. So that is an example, but there are going to be more and more such examples for us to be able to use prosthetics to mimic part of the brain, in addition to computers developing the ability to behave like a brain. So technology and the ability, for example, to optogenetically stimulate different parts of the brain and see what happens, along with the growth of computers, is going to give us an understanding. There are huge technological challenges, but the pace of change is so fast that I would not hasten to put a long time limit for how we're going to see changes of a very dramatic manner. Now, this is the connectome. We know this is the brain of a fly, and this is a connectome of every single nerve cell in the brain of the fly. There are about 45,000 or so, 49,000 nerve cells, and they make millions of connections, as opposed to our brain, which has got 86 billion nerve cells and makes trillions of connections. This works to do very complex tasks, much the same way in which our brain does complex tasks. The difference is, this is specialized to do only a few things really well. The fly can fly, it can, find its mate, it can make more flies, it can evade your swatter, and so on. It can do those things brilliantly. We can't do those things the way the fly does. For us to fly, we need to make an aeroplane and then fly. The fly can do it right after it's born without any problem, right? But we have such a wide range of other capabilities because of our much more huge parallel computer that we can do many things badly intrinsically, but because of the way we have developed our software, we can use prosthetics, create technology, create language, and become stewards of the planet, as Dan pointed out. So our ability and our understanding of how each nerve cell works in the brain to allow this software to function is getting better and better. So far, our interventions and our understanding are relatively crude. And they are crude in the sense that they try to affect the entire organism, the entire animal, and try to manipulate. This will get better and better, and our understanding both bottom up in how anatomy and physiology impacts on behavior, and top-down about what goes on inside as a consequence of specific behaviors will get better and better. So I'd like to end by saying that we have a very crude view of the brain from our textbooks, that this part does that part does that, and so on and so forth. Right? And that is true. There is a lot of specialization. But its ability to have layers talking to each other and feeding back to each other, thinking about what you're thinking about what you're thinking about what you're thinking, is something which is unique to human brains and has transitioned from these kinds of brains to our kinds of brains in a dramatic way. We've learned a lot from evolution about how our anatomy and our physiology and our chemistry is made. But we also need to learn about how our societies work and how cultural change, language, is layered as software upon this and how they're dramatically changing both us and the world. Thank you very much. Sure.
Thank you so much, Dr. VijayRaghavan. We also wanted to open the floor for some questions, if anyone has any. There are some young men circulating with mics. We'll go. Any questions here? Okay, we have one there. In the corner.
What about Elon Musk's neural network?
Sorry?
Elon Musk's neural network.
Yeah.
What
So,
was it about that?
So, amongst
The neural network of
Yeah.
Elon Musk.
amongst his multiple achievements, which are equally balanced on the other side, Mr. Musk has developed something called Neuralink, which allows the kinds of prosthetics I talked to you about to be implanted. In principle, again, those are the kinds of interventions over a long term will develop to have enormous impact. At this stage, they are extremely small in number and poor in our ability to analyze that because the information is not fully there. But the idea that you could implant stimulus in the brain and therefore affect behavior is not a new one, it's an old one. He's trying to do it in a more refined manner, and I'm sure that as time goes on, we'll see more interesting things. But it's very, very early stages now. Yeah, up to that.
Hi, Vijay. Yeah, it's a wonderful talk. Yeah, so my question is, what is the fundamental difference between the machine learning and the learning by a kid?
But
By a kid
yeah,
at their childhood?
yeah. Well, the short answer is we don't know. But what little we know points to very similar mechanisms. And the mechanisms are broadly of two kinds, well, three components. One, there are multiple layers which are at work in assessing the environment and responding to it. Errors are made depending on experience in that response. That errors allow different weights to be assigned to inputs so that the next time you see or hear or touch certain phenomena, you respond without having to go back to the same experience again, right? And therefore, this ability to make guesses about the future and not having experienced that future and make guesses depending on what other different, very different situations you've experienced is a very human trait. A human will not walk off a cliff just because a road said, please go straight, right? A kid might do that, right, with dangerous consequences. So this ability to distinguish, what should be done in terms of what sensory inputs you get and override some of that is an adult response which gets better and better. Kids are not good at that, but adult humans get better and better. Machines also get better. So there are lots of fundamental similarities, in other words, though the structural ways the brain is an analog computer, and the computer is a digital computer, and they function in very, very different ways, many different energy requirements. But the layering and the way they function is very similar. Yeah.
It's a very thought-provoking talk. So I have a couple of questions. First question is, compared to invertebrates, we have largely lost our regeneration abilities.
What?
Regeneration abilities, nerve regeneration
Right.
abilities. But we might have gained some cognitive abilities. How do you explain in terms of evolution that thing?
So, as I said, our gain in cognitive abilities is a...
But we have also lost, like we can't regenerate, except some of organs like liver. We cannot do nerve regeneration, like earthworms or like other invertebrates.
Yeah, the gain in cognitive function, first of all, is not only a biological property. It's a cultural property. Now, about regeneration, there are no shortage of tissues in our bodies which regenerate. Skin, liver, and so on. And there are no shortage of tissues which can be made to regenerate. Spinal cord regeneration, for example, there are enormous advances. Now, why regeneration is there only in some contexts and not in others is a very important evolutionary question. But it's not a question which is a unique one for humans versus other animals. There are many animals which don't regenerate parts and other animals which regenerate very easily.
Thank you.
Or plants for that matter.
And the second question is, you said like the toolkit is same for all. Then what is the core of our individual differences in abilities?
Our individual differences.
In humans. Yeah.
Well, you've asked a deeper question. One is, what is the difference between species? How do we make, with the same toolkit, different species? Why is it that we accidentally don't use the toolkit to make a different animal altogether? Because the toolkit is the same, you could end up doing that. And the reason is that how you play out the orchestration of gene expression is a context-dependent phenomenon, depending on what the cellular and the external environment does. So a bear always gives birth to a bear and not to a leopard, even though the toolkit may be the same. In an airplane factory, you make a Cessna or a Boeing, you don't suddenly decide to change your mind. No, yet there are individual variations, and that's a very, very important thing you mentioned. I'll take a couple of minutes to that, because there's a trivial answer to that, saying that, oh well, you know, there are differences in genes or gene expression, but it's a little more than that. Alan Turing invented a computer which, if given enough memory, could compute everything, the stored program computer. Von Neumann invented a computer which could replicate itself, but he also spiked it with the possibility that this computer could make defects, and therefore the progeny of a computer could be different from itself. And selection then applies, and different kinds of computers come along. Now that happens, of course, to create speciation in the